Okay, let's go ahead and get started. I'm just going to duck the lights real quick. Today, I really want to try and devote as much time as possible to our matrix analysis problem. I want you to have a general understanding of how Math 10 and other software packages work. So we're going to do this example start-finish today, but we're going to do a mix of some board calculations and some calculations in Excel. If you go to Blackboard, you'll see I have an Excel template developed, ready for you to make life a little bit easier. So I'm going to go through that template sort of first, then we'll spend the rest of the class going through the in-class example. Did everybody get the QR code?
I was getting accused of murder, sorry.
I did not do that.
I didn't say you did.
Okay.
I did.
Okay, now that it's clear. All right. Okay, everybody. So, today we're going to be using Excel to do matrix analysis, to do matrix algebra. Just to make sure that we're all on the same page, this is going to be our procedure for doing matrix analysis. We're going to go through this procedure today, but essentially it's broken up into 4 parts. So the first thing we're going to do is we're going to assemble the K matrix for the system as a whole. We're then going to assemble the F vector, the force vector for the structure as a whole. We're going to solve for our displacements, and we're going to back calculate. Now, just a little bit on notation, and I put this here on the board. I was very specific in how I named things, so it wasn't me not capitalizing certain terms. But just so everybody's clear, whenever I put something here on the board or whenever I do any computations, if I'm using a lowercase letter, so in other words, if I'm using a lowercase f or a lowercase k or a lowercase delta, that refers to an element by element value or an element by element matrix. But if I'm using an uppercase f or an uppercase delta or an uppercase k, so I use these little serifs on my k's, that corresponds to the structure as a whole. Okay? So just to be clear, and I'm going to stick to that. So if you see me using an uppercase letter, that's for the entire structure. Okay? All right. We talked a little bit about matrix algebra yesterday, just to make sure that we're all sort of remembering this. A lot of the matrix algebra that we do today, we're going to do in Excel. So that's really going to sort of be our focus for at least the first little bit. And there are 3 computations that I'm interested that you're familiar with, and that is the transpose function, the matrix multiplication, and matrix inversing. To be clear, we're not going to use transposition today, but we'll use that when we come back from break. And we're going to do it in Excel. Excel is really nice for matrix analysis, as we're going to see, because matrix analysis for this is a very visual process, specifically the assembly part of matrix analysis for structures, and in Excel that works very, very nicely. Okay, so there are 3 operations that I want to make sure that we're clear about. The first is what's called a matrix transpose. So if you look at this nice little animation I've got here, so if you see here, this is a matrix. If you transpose it, or in other words, you sort of reflect it about the main diagonal, that generates the transpose. Okay, and we're going to do transpositions when we come back from break. But the 3 operations that I'm really focused on today are transposing, multiplications, and inverses. Okay, and just to show you how this works, this is really, really basic. Let me go here. So if you open up the Excel sheet that I posted on Blackboard, there's 2 tabs. The first tab at the bottom is your matrix. It's just to sort of make sure we're comfortable with this. So it's this tab called Array Commands. That's sort of how it's referred to in Excel. And I'm not going to do all of these. Some of these are really easy. So for example, if you want to add A plus B, I think the easiest thing to do is just that plus that. Just do it on a term-by-term basis and copy and paste. And we'll do that today, but that's pretty easy. Okay. The big thing, though, that you want to be comfortable with are the matrix, the other matrix-style computations. So just to show you how this works, okay, let's just do the inverse. Okay. So I have A inverse that I want to compute, and the formula is M inverse. Okay, so what you'll do is you'll say equals M inverse, put your cursor in the top left corner of where you want the matrix to go, M inverse of this matrix and just press enter. And what Excel does is it fills all of the other cells for you, okay? So for example, you'll see that these cells are filled up and we didn't put a formula there, okay? So one thing just to be aware of, I can type a number here, but Excel will get angry at me, okay? Because it's like, wait a minute, I need that value to deposit the inverse matrix, okay? So if you want to do matrix multiplication, the formula is mmult, so we just do equals mmult of this, comma, this. So you don't use like the asterisk that you use to multiply numbers. You don't do 2 asterisk 3 to multiply 2 numbers. You do mmult array 1, comma, array 2, press enter, and it fills up the rest of the cells. Okay? The big thing to keep in mind, again, put the cursor in the top left corner where you're going to go, and just make sure you follow your commands. Don't worry, this is going to be a pretty easy process for today, and we'll take our time with it. Okay, is everybody okay with this? Is this part easy? I'm hoping this is pretty simple. And again, over here on the right, if you want to practice them, I've basically put the answers for all these problems. This one down here on the bottom, we are actually going to do this when we come back from break. This A transpose BA, we will do computations like that, but that's a post Thanksgiving break problem. Okay, everybody good? All right, so let's talk about this problem. Okay, we didn't get a chance to do much with this problem yesterday, so I really want to make sure that we focus the majority of our lecture to try and solve this problem start to finish. Okay, so let me pull this up in the notebook, and I kind of want to make a few points about this. All right, so I've got the problem drawn up here on the board, okay, and here's the problem. So I've sort of drawn it in 2 fashions here on the board. I've got the structures, and then I've got this like analytical model down here, and I'll refer to that a little bit as we do the problem. But for each element, notice how I've got the EA and L values, EA and L, EA and L. Now, one of the things to note in matrix algebra, and we've started to notice this in the project because you have to do this in consistent units, is just that. You have to do it in consistent units. So notice here on the board, I didn't even bother saying that this is 10 feet long. It's 120 inches long, okay? This is in inches, this is in inches, this is in inches. This is in kips, this is in kips. Everything's in kips, everything's in inches. So all of our units are consistent. We have to basically accept a consistent system of units at the beginning, and then we sort of just barrel through it, okay, and let the answers be the answers. Okay? Everybody with me on this? Now, everybody should have their nifty little matrix handout, which we're going to follow today. So we're going to go through each of these parts one by one. So one of the things to note is that for each element, okay, so let's talk about this problem and let's plan it out, okay? So each element is going to be a 2x2 matrix, okay? And how are we going to calculate that 2x2 matrix? Well, it's pretty easy. It's right here. That's one of the beauties of matrix analysis for finite elements, is that computing the stiffness matrices is not something we need to derive over and over again. Once we have the problem, we have it, okay? All right? Now, that's for each element. So element number 1 is going to have a 2x2. Element number 2 is going to have a 2x2. Element number 3 is going to have a 2x2. That's for each element. For the system has how many joints? It has 1, 2, 3, 4. And when I say degrees of freedom, what I mean is the different ways that these joints can move. So theoretically, this joint can move left or right, so that's a degree of freedom. This one can move left or right. This one can move left or right, or this one can move left or right. So the structure as a whole is going to be 4 by 4, okay? And the way that we get from an individual stiffness element, or stiffness matrix for each element, to the stiffness matrix for the system as a whole is this process called assembly. And we'll get to the assembly process in short order, okay? The last thing that we're going to have to do is we're going to have to figure out the force vector and the displacement vector. And because we're looking at the system as a whole, remember capital letters are for the system as a whole, this is going to be 4 long, or more specifically, 4 by 1, okay? Now, the nice thing about these force vectors and these displacement vectors is we can actually just sort of look at the structure and write these down, okay? In fact, let's do that, okay? So, let's see if we can come up with a force vector for the structure as a whole, okay? So, basically what we're trying to do is we're trying to write down what are the forces at each of these joints. Some of them we know, some of them we don't. For example, at joint 1, I do not know what the force is because that's where a reaction is. So I'm going to call this reaction 1. I don't know what that is. Okay? I'll do my curly brackets in the end. Okay? That's R1. In the case of joint 2, there is a load that's applied. That load is 300 kips. Okay? So I'm going to write this down as positive 300. Now, why am I writing this one as negative 125? Why am I writing it as negative?
It's going in the opposite direction.
It's going left, right? Remember, we say, here's our coordinate system, and we say forces to the right are positive, okay? So this is a positive 300, this is a negative 125, and down here, we have our 4. So this is our force vector. That's pretty easy. We can just look at the structure and write it down, okay? What about the displacement vector? Well, the displacement vector sort of takes like a checkerboard pattern to this. So what do I know about the displacements? What are the displacements going to be? Are there any displacements that I know? What's the displacement here? Can this point move? No. So this displacement is going to be 0. Then I'm going to have delta 2, delta 3, and then another 0. So that's going to be my force vector and my displacement vector. They're really easy to figure out. You can just sort of write them down. All right. Does that make sense? Everybody okay with this? All right. What's it?
Are we just assuming R1 and R4 are both positive for now?
For now.
Okay.
For now. They might not be. They might not be. We're going to find that out. Okay. Everybody with me so far? Everybody with me so far? Okay. So let's go through a couple things. I'm going to take my keyboard off real quick. So, and my apologies in advance. I might be doing a little bit of hopping back and forth between my notebook and Excel, but you'll see what I mean. Once you sort of figure out the process, you'll see it's pretty straightforward. Okay, so let's start off with element number 1. Okay, so we're doing part 1, which I'm just going to call part 1 assembly. Okay, so let's do element number 1. All right, so the first thing I need to do is I need to come up with a K-matrix, a little K-matrix for that element. Okay, so the way I'm going to do that is I'm going to calculate EA over L, which is 2,000 times 6 over 120, okay? And 2,000 times 6 over 120 is going to be 100, right? So therefore, my K1 is just that. All right, because see what it is? It's just whatever that value is, 1 minus 1 minus 1, 1. It's just that. Easy, right? Okay. Everybody with me so far? Okay. So let me ask you a question. Now let's look back to the structure as a whole. Okay. This is element number 1. This is element number 1. Which joints, which nodes are element 1 connected to? 1 and 2. Does everybody see that? So what I'm going to do for this calculation is I'm going to say 1, 2. 1, 2. Okay? I'm going to indicate those codes right here on the system, okay? And again, what I want you to think about is this is what happens when you click the little solve button in Math10. Math10 is breaking down the problem this way, and this is how it's doing it. Now, all right. Now what I want to do is I want to do the process of assembly, okay? Does it make sense that the K matrix for the whole structure has to be 4 by 4? Does that make sense? Because we've got 1, 2, 3, 4, right? Okay. Well, this part's really easy and really visual, okay? So now what I'm going to do is I'm going to take this little K matrix and I'm going to turn it into a big K matrix. And the way that I'm going to do that is I'm going to have a big matrix, and I'm going to have 1, 2, 3, 4. 1, 2, 3, 4. And what I'm going to do is, it's really easy, it's really basic. I'm just going to put these terms where they go over here. So I'm going to put 100, minus 100, minus 100, 100. And so, what else goes in this matrix? Zeros. Now, why am I doing that? Okay. We're looking at element number 1. Element number 1 is right here. I propose that element number 1 by itself contributes no stiffness over here. It's only contributing stiffness here and here. So I am only placing those stiffness terms where they go in the system as a whole. Does that make sense? Okay. Everybody with me so far? Let's hop to Excel. All right. Okay. So here's my Excel sheet, okay, and let's see if we can work this out. So here's my little k for element number 1, and by the way, I went ahead and did the little k for element number 2 and element number 3, okay? Now I propose what I need to do is I need to put those terms where they go. So what am I going to do? I'm going to put this value here, put that value there, put that value there. Okay? And you could just leave it like that. If you want to put the zeros in, you can. I'm actually just going to leave it like that. I propose that this element goes right there. Okay? Now what about element number 2? Okay, element number 2, I've got to take 3,000 times 8 divided by 120. That ends up being 200. So 200, here's this, 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 and this. Okay? Now where does that go inside the system? Where does that go? Goes right here, doesn't it? Where the 2 and the 3 is. 2 and the 3. So element number 2 going to go here. Does that make sense? So an interesting finding is that if I were to compare this matrix and this matrix, does everybody see how these two terms are in the same spot? Everybody see that? See how for this matrix I've got a term in 2, 2, and this matrix I have a term in 2, 2. What I'm going to do for the assembly process is I'm going to add this up term by term, and these terms are going to add up. Does that make sense? I propose yes. Here's why. If I grab this node, like with my hand, and I try and push it this way, I have to stretch this spring and compress this one at the same time. So those stiffnesses are going to sum up at that point. Does that make sense? Okay. So if we're all paying attention, tell me what I do here. What happens with this one? This is element number 3 right here, connected to joint 3 and joint 4. What do I do?
At the 3 and 4 and the 3 and 4.
They're going to go down here. So, what is the process of assembly? Here's what the process of assembly is. What I am doing is I am taking these terms, I am putting them where they go in the global stiffness matrix, and then I am summing it up term by term. So how do I get the big old K matrix? I say equals that plus that plus that. Just term by term by term. So this right here is the 1-1 term, the 1-1 term, and the 1-1 term. And if it's blank, it's blank. Just sum it up on a term by term basis. Enter. Drag across the board. And that, ladies and gentlemen, is the global stiffness matrix for this system as a whole. So we've got some 300s in here, and that's where those terms overlap. So maybe I'll show that here. I'll say that this term and this term, they overlapped as well. So anytime there's a term that overlaps, you just add them up. What do we think? Can I show you a nifty little trick to check your work? Watch this. Let's take the K matrix. What's that plus that plus that plus that?
0.
What about that plus that plus that plus that?
0.
What about that plus that plus that plus that?
0.
Along every row and every column, the K matrix will sum to 0. And I'm saying this because, like, in a really, really big system, this is an interesting way of just checking to make sure your work is correct. Make sense? By the way, okay, so here's my F vector. So I'm going to say R1, 300, minus 125, R4. That's what we said, right? Is that okay? Is that okay?
Yes.
Okay, now, can I go back to the notebook for a second? I'm sorry that I'm hopping back and forth on the notebook. I can't really avoid it with today's lecture. Everybody got this? Okay. All right. Okay, so what I'll say is in Excel, we did the following. We computed KE for each element. We assembled to get K for the system as a whole, and we wrote our F vector. So now what? Okay, let's go to our handy dandy little guy here. So, what is part 1? Part 1 is we develop a stiffness matrix for each element. Done. We assembled that into a stiffness matrix for the whole system. Done. Part 2, we have developed our structural load vectors. Done. So we've already done part 1 and part 2. Okay? So now what we need to do is solve the system. Okay? So how do we do that? All right? We've got this little statement here where it says we apply our boundary conditions. So let's apply boundary conditions. Okay, let's write our problem as a whole right now. So this is K delta equals, actually, delta. Let's write K delta equals F. Let's just write the whole thing out. So what do we got? We've got 100 minus 100, 0, 0, minus 100, 300, minus 200, 0, and then it's 0, minus 200, 300, minus 100, 0, 0, minus 100, 100. We have our delta vector right here, 0, delta 2, delta 3, actually, hold on. 0, delta 2, delta 3, 0. I want this all to like line up as well as I can. Equals, and then this is R1, 300 minus 125, R4. Okay, so this is the system as a whole. Okay, I'm going to cheat a little bit and so I copy and pasted the system, so I just have it again. Okay, so let's apply boundary conditions. So what does this mean in MathCAM? Okay, so think about modeling in MathCAM. Okay, so you create the geometry, you define the nodes, you define the elements, right? So MathCAM can compute the length of each element based on the nodal coordinates. You assign the geometry in the section, okay? Or sorry, the material in the section, So we've got the geometry, the material, the section figured out. What about our conditions? Well, the two conditions we have are our loads, but also our fixities. We haven't talked about the boundary conditions. We haven't actually done anything with that yet. And the boundary conditions are here and here. What do we know about this problem? We know that delta 1 equals delta 4 equals 0. So how do we handle that? I'm going to show you how we handle that. It's really easy. What we do is, so what do we say? This is 1, 2, 3, 4, 1, 2, 3, 4. All we do is we strike out row 1, row 4, and in our stiffness matrix, strike out column 1, strike out column 4, and that's it. Okay, that's how we apply boundary conditions. Now, that's how we do it. Here's why. So, the reason that we are able to strike out the columns is because when you do your matrix multiplication, these terms and these terms are going to be multiplied by zeros. So they're like when we carry out this whole multiplication, this is 0. Because this is 0 and this is 0, these will all get multiplied in terms of zeros anyways. The reason why we're able to strike out the rows is because those are separate equations that we are going to use later. Right now we don't need them. Later on we will. And so what we're going to be left with is this matrix, this vector, and this vector. And this is going to be KR, delta R, FR. Okay. And so now we have this smaller, reduced system to account for the presence of boundary conditions. All right? Does everybody have this written down? I'll give you a sec. Everybody good? All right. So let's go to Excel. So here's my Excel. This is what I like to do. We're doing row and column 1 and 4. So what I'll do is just take row 1 and sort of darken it out. Take this, darken, 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 and so the values are still there. It's just I've darkened them up a bit. Okay. All right. So now I've got a KR and an FR. Let me open up my Excel file, and I think we can probably stay in Excel for the rest of the lecture. I think we can do it all here. So what I'm going to do is I'm just going to say equals all that, and say equals that. Okay. I'm going to give everybody a sec to catch up with me on this. And if it's okay, I'm going to erase this part here on the board. Okay. Is everybody caught up with me? Everybody caught up with me here? All right. So this is where we're at right now. We have KR delta R equals FR. What I want is this. Okay? So the way I'm going to get that is I'm going to say delta R equals, instead you can't divide by a matrix, but what you can do is multiply by the inverse. So everybody watch up here. This is probably the hardest thing in the whole lecture. So we're going to go here. We need to do a matrix multiplication. So we're going to do mmult, and we need to multiply two matrices. The first matrix is not this one. It is the inverse of this one. And the second one is that. So it's going to be mmult M inverse of K R comma FR. That's going to be our expression. And then when we press enter, we should get that. I'm going to give everybody a sec on this. This is probably the hardest part of the whole thing. By the way, is this seeming to be very difficult? Okay. So, here's something I'm going to do here on the board. let's write down some answers to this problem. Did this give me some answers? I think it told me that this joint displaces 1.3 inches to the right, and this joint right here displaces 0.45 inches to the right. Is that a fair statement? There's some answers. Okay. All right, let's keep going. Now, what do I got here? Okay, this is kind of nifty. Let's watch this right here. So I've got K, instead of delta, I put D. K, D, and F. So let's start off with K. Well, K, I already have that figured out. That's just all this. I'll just, copy and paste all these down here. Now, what's the D vector, or delta vector? The delta vector is the displacements for the structure as a whole, okay? And what that's going to be is 0, this, and 0. Right? So just take these values, put them in a big old vector. Okay? And this right here, this is essentially our step 7. So basically, take these deflections and come up with a big old delta vector. So what do we have left to do? Okay. Well, here's something we can do right here. I can take K times delta. Let's just do that. So, equals M mult K and delta. What did this accomplish, by the way? What was the value in doing that?
Do the reactions.
It gave us the reactions, right? Because what did we have? I mean, what did we originally say the F vector was? We said it was R1 plus 300 minus 125 and R4. And what did it give us? It gave us a force, 300 minus 125, and a force. So, what answers did we get? We got that R1 is, what, 130 kips to the left. R4 is 45 kips to the left. Is that a fair statement? Can I ask you a question? What's the sum of these values? What happens if you add these four numbers up? What do you get?
Probably 0.
It's almost like the sum of the forces in the x direction equals 0, isn't it? It's crazy, isn't it? So, what's the only thing left? This. Okay, and what are we doing here? Basically, what we're doing is this was K times delta for the structure as a whole. Now we're going to do K times delta for each individual element. So how do we do that? Well, we've got the K's for each element. Now we need to come up with deltas for each element. So how do I do that? Well, anytime I see a 1, put a 0. Anytime I see a 4, put a 0. Anytime I see a 2, make it 1.3. Anytime I see a 3, oh, that was negative. Anytime I see a 3, make it 0.45.
Hey, Dr. Mike.
Yeah, what I do?
My Excel does not look like that.
Does not like what?
Like where it goes K1, D1, F1, everything under that is not there.
This is all here?
Everything under K1, D1, and F1, not there.
This isn't here. This.
Yeah, and then the ones to the right of it.
So if it's missing, just do this. Just hit equals and then just go up here.
There's actually something in place.
Is everybody else having that issue?
What?
Is anybody else having an issue down there? Sure. Just hit equals and copy those from down there. Let me see.
he has a random, like, graph. I don't even know where he got that from.
I don't know where it came from either. So like I've got the top three and then these just.
Whoa. All right, hold on. Here's what we'll do.
Okay.
Let's just do this. I don't know what all this, I don't know what all this is, but we'll just do this. Something happened. I don't know what happened on your file.
I don't know.
I think you accidentally copy and pasted something somewhere.
I mean, it's possible.
And then just delete and then copy this up.
Okay.
Okay. So I think everybody's sort of following along, but what we're going to do is we're going to do equals m mult of this and that. And then I like copying and pasting, so I'm just going to copy and paste here and here. So in MathCAN, does anybody remember a quick way of telling whether or not an element's in tension or compression when you look at the forces? Say it again? The sign, but if an element has two responses, which one do we look at? The second one, right? So the second one will tell us if the element is in tension or compression, right? I mean, think what's happening here. I'm going to erase this over here. So let's take element number 1. Okay, element number 1, I'm getting a negative 130 over here and a positive 130 over here. So element number 1 is experiencing what? Tension, right? What about element number 2? Element number 2 is experiencing a positive 170 and a negative 170. What is element number 2 experiencing? Compression, right? So is it fair to say that element number 1 is 130 kips in tension? Element number 2 is 170 kips in compression, and element number 3 is 45 kips in compression? Is that okay? Take a look at what's in this box right here on the board. Take a look at that. I mean, what do we have? We have the deflections everywhere. We have the reactions everywhere. We have the internal force in every member. We have every result, all of it. One method, the whole problem is solved, everything. This is what MathCAN is doing, okay? What it's doing is it's breaking the problem down, writing a stiffness matrix for each element. It's assembling that into a stiffness matrix for the system as a whole. It's writing a force vector for the system as a whole, knocking out the rows and columns associated with boundary conditions, solving, and then back substituting. That's what it's doing. Now, this problem is one-dimensional, okay? In other words, everything's just going left and right, okay? What if I took this problem and the only thing I do is just add up and down? That's it. Just take the same mechanics, the same behavior, and instead of just left and right, just add up and down. Instead of a bar problem, that's a truss problem. That's how MathCAN does trusses, okay? And what is the difference between what we're doing now and trusses? Trig. That's the only difference. Just throw in some sines and cosines in there. That's it. That's the only difference, really. So if you take this, throw a little bit of trig in there, you are getting how MathCAN does truss analysis. That's it. Okay? Does anybody have a question? All right, I want to show you your homework assignment. It's going to look crazy, I promise, but it's pretty easy. Okay. And this one was off the dome. Okay.
We should get off the book.
So I could go
Look into
to the back of the
book.
book.
Yeah, you ain't getting that one on this one.
Tried.
Okay.
Let's try.
So, I'm going to give you a slight hint on this one to make things a little easier. Okay. So, there are two problems on this assignment. Problem number 2, you aren't going to be able to do when we come back from break. But problem 2 is very plug and chug. It is the most plug and chug problem I've probably given you this whole semester. So when you come back from break, the assignment's not due till Friday of debut. Like you've got plenty of time. This is the last homework in here. Just to be clear, it's not due till December 5th. So you got plenty of time on this assignment. Yes.
You drop our lowest homework grade, right?
I do not do that.
Tennessee may not do this one. We did.
I was just wondering.
I don't drop the lowest homework. Where'd you come up with that?
Other teachers did. It was a curiosity thing. Sorry.
Greetings, everyone. My name is Dr. Other Teachers.
No, they're not doctor.
No, but guys, there's also so many of these things that, you know. All right. Okay. So this problem, okay, everybody pay attention. This is important. Okay, this problem is the exact same problem that we just did. It's just arranged differently. Okay, so it looks different, but it's really not that different. Okay, so I propose that this problem has 6 elements. So there's element 1, 2, 3, 4, 5, and 6, and those are going to be the springs. And for the joints, I want you to treat these blocks as the joints. Okay, so the system's being loaded left and right, and you're going to tell me what the displacements are. So to give you kind of a hint, okay, let's take element number 5. Okay? Element number 5, we need to write the stiffness matrix. Okay? I give you all the stiffnesses down here. Okay? So element number 5, I'm telling you that the EA over L is 7. Okay? So element number 5 is going to be 7, minus 7, minus 7, and 7. That's the element. Okay? As for its assembly, okay, element number 5 is connected to joint 3 and joint 5. Okay? So when you assemble this, the structure has 5 joints overall. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this was going to be K5. All you're going to do is just put it there. Okay? That's all you're going to do. And I'm just using one element as an example, but they're all going to be the same way. Okay? Just put the terms where they go. It's no different. Okay?
Mike, pose for the camera. I'm putting that on Facebook.
Please, dear God, don't do that. Okay. Any questions?
If you drop this homework, I won't put it on Facebook.
That's a statement.
I guess I'm meta-bound. I guess.
Yes, you're.
Mark Zuckerberg has his ID.
All right. Hey. In all seriousness, okay. So I'm going to be around. Like I'm going to be around for the next, obviously the next couple days. And Friday we don't have like a formal class, but I'm going to come in, and my goal is just if you all have Q&A on your homework or on your project. If I don't see you, have a wonderful break.
You too.
If not, I will see you on Friday. So.
We don't have class tomorrow. If you're curious.
fine.